Present the conference. Bender's theory for discrete subproblems. Bender's Gomory cuts. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. Since its formulation in 1962, the researchers in Bender's theory, BT, have proven that BT is an effective methodology to solve complex problems that cannot be solved using only best basic optimization algorithms, Plex, Gurobi, Express. Algorithms based in Bender's theory can solve NP-hard, non-deterministic polynomial time problems in reasonable time. For this type of problems, BT has proven to be an effective methodology to solve complex problems that cannot be solved using best mathematical solvers. BT is a mature methodology that is in the accelerated growing phase, and there is a gap between the research in mathematical programming and the application of the large-scale methodologies in real-world solutions. This presentation focuses on Bender's theory for discrete subproblems. Discrete subproblems. Bender's theory. In mathematics, the convex envelope, or convex shell, or convex hull of a set of points x of dimension n is defined as the intersection of all convex sets containing x. The graph shows the convex envelope of the feasible zone of an integer program. Rounding up a continuous solution doesn't yield any useful results. In the case of points in a plane, if not all points are aligned, then their convex envelope corresponds to a convex polygon whose vertices are some of the points of the initial set of points. An intuitive way to view the convex envelope of a set of points in the plane is to imagine a stretched elastic band that encloses them all. When the elastic band is released, it will take the shape of the convex envelope. The image presents several examples of a two-dimensional convex hull. In computational geometry, there are numerous algorithms for calculating the convex envelope of a finite set of points, with varying degrees of computational complexity. The complexity of the resolution algorithm is usually estimated based on the number of entry points, and the number of points of the corresponding convex envelope. Some algorithms for the calculation of the two-dimensional convex envelope are listed. Bender's Gomory cuts. Ralph Edward Gomory, born May 7, 1929, is an American applied mathematician and executive. Gomory worked at IBM as a researcher and later as an executive. During that time, his research led to the creation of new areas of applied mathematics. The Gomory cutting plane method is a procedure for finding integer solutions to a linear problem. It works by initially solving a non-integer, continuous, linear program, then checking whether the optimization found is an integer solution. If not, a new constraint is added that removes the non-entire solution but does not remove any other points in the workable region. This is repeated until the optimal integer solution x is found. Gomory cutting planes redefine the continuous feasibility area by an integer convex hull that contains all the integer solutions of the continuous feasibility area, and whose extreme points, in the optimum, correspond to an integer solution. Gomory created his method in 1958. To solve the problem, a structure of two levels is established. In the first level, is considered the equivalent problem in terms of y, that is designated coordinator. In the second level, a problem for the variable x that generates extreme points for the coordinator problem. The solution is obtained exchanging information between the coordinator and the subproblem. The coordinator proposes values of y and the subproblem generates extreme points or dual variables. In the case of subproblems with integer variables, if the matrix A and the vector B minus f, y, they have only integer elements, it is possible that without the need for manipulation the subproblem produces integer solutions. In the case of subproblems with integer variables, or binaries, we can use Gomory's concepts to construct a linear problem equivalent to the integer programming problem. In the solution of the subproblem, in a first step the linear problem is solved by relaxing the discrete character of the variables. If the solution is complete, the coordinating problem is returned. If it is not, Gomory cuts are introduced until the linear problem is solved with integer solutions. When the solution is obtained, the Bender's cut in the coordination problem is generated. In the case of subproblems with discrete variables, we can use Gomory concepts to build a linear continuous subproblem equivalent to the MIP subproblem. In solving the subproblem, the first step is to solve the linear problem that relaxes the discrete character of the variables. If the solution is feasible, the control returns to the coordinators problem. If it is not, GCPs are introduced. When the feasible solution is obtained, a Bender's cut plane is generated on the coordinators problem. The values of the dual variables of the subproblem are valid because they was generated by an equivalent continuous problem, and the generated Bender's cutoff is valid. The figure presents a flowchart of the implementation. There are several algorithms for solving MIP subproblems. Ralphs and Hassanzadeh, in 2014, presented a review of the main approaches for solving two-stage mixed stochastic linear programming models, which have discrete variables, including the case of a pure integer second-stage problem. Gate et al., in 2014, presents the speedup provided by the ITS proposed methodology compared with Plex solver. The problem application was the stochastic server location problem, SSLP. It is evident that Bender's ISP is faster than Plex. The paper a modified Bender's partitioning approach for problem having discrete with applications to integer recourse stochastic programs presence. An approach to solving discrete optimization problems that generate integer subproblems, such as those that arise in the case of two-stage stochastic programs with an integer resource, using concepts from the reformulation linearization technique, RLT, and lift and project cuts, LPC. The convex representation of the convex hull of the restricted region of the problem is available when the binary is applied only to the resource variables of the second stage, then the regular Bender's algorithm, BT, is applied. The procedure is based on sequentially generating an adequate partial description of the convex representation as needed in the process of deriving valid BT. The key idea is to solve the subproblems using an RLT or LFC but to generate, and store, the cuts as functions of the first stage variables. Therefore, the cutting planes can be reused from one subproblem solution to another, simply updating the values of the decisions of the first stage. The proposed Bender's cuts also recognize these RLT or LPC as functions of the first stage variables, and are hence shown to be globally valid, thereby leading to an overall finitely convergent solution procedure. The approach is based on a priori generation of the convex hull representation. If the size of the problem permits, if it has few integers variables, then this is a viable option, and leads to a usual application of Bender's decomposition. Otherwise, it is possible to generate a partial representation for Z as needed in a sequential convexification process. Higl and Sen, in 2000, have proposed an alternative sequential convexification process based on a different cut plane approach to solve the subproblems, that it is used as key concept in the development of the proposed solution process. The goal of the stochastic program is to optimize the first stage costs plus the expected recourse costs. Some notable applications of stochastic programming include scheduling, Burge and Dempster, in 1996, financial planning, Carino et al. In 1994, power generation, Murphy et al. In 1982, facility location, Laporte et al. In 1994, and vehicle routing, Laporte et al. In 1992. For more information on stochastic programming in general, we refer the reader to recent books on stochastic programming by Burge and Louveau, in 1997, and Colin Wallace, in 1994. There are several popular methods for solving two-stage stochastic LPs with recourse, and most of these rely on the underlying principle of Bender's decomposition. The inherent structure of these problems lends itself to a natural partitioning of the variables. The first-stage investment, resource acquisition, or location-type decisions represent the complicating variables, and the subproblems determine the best recourse actions for any given first-stage decisions. There are several popular methods for solving two-stage stochastic LPs with resource, and most of these are based on the underlying principle of Bender's decomposition. The inherent structure of these problems facilitates a natural partitioning of variables. Decisions on first-phase investment, resource acquisition, or localization account for the complicating variables, and subproblems determine the best resource actions for any first-phase decision. A common practice is to approximate continuous distributions with discrete ones, which allows the expected resource function to be calculated as a simple weighted sum. In the case of stochastic programs with integer resources, Schultz in 1995 showed that, under smooth conditions, discrete distributions can effectively approximate continuous distributions with any given precision. The image presents the formulation of Shirali and Fraticelli's model. Flowchart of the implementation for the proposed Bender's algorithm. The image presents the formulation of a toy example, used to clarify concepts. To illustrate the concept of the proposed approach, suppose we have a relaxed master program, RMP, that currently exhibits Bender's inequality. This problem results in the solution x equals 1 and y equals -3. The paper Decomposition Algorithms with Parametric Gomory Cuts for Two-Stage Stochastic Integer Programs, authored by D. Gade, S. Kusukiavius, and S. Sen, was published in Mathematical Programming in 2014. In it is modified Bender's decomposition method using reformulation linearization technique, RLT, and lift and project cuts, LPC, to develop a new method for solving discrete optimization problems that yield 0 to 1 mixed integer subproblems, such as those encountered in stochastic programs with integer recourse. Considering the convex hull problem, it is demonstrated how cut planes could be generated to derive a partial description of the convex hull as needed to design a finitely convergent solution procedure. It is important to note that the classes of cuts used in the subproblems are derived as a function of the x variables of the first stage, allowing them to be reused in subsequent subproblems simply by revising them according to the corresponding solutions. In addition, globally valid Bender's cuts are obtained by recognizing these cuts as functions of the variables of the first stage. The ability to reuse cut planes from one subproblem to another is useful from the point of view of reducing the computational effort required to solve discrete subproblems, while improving the lower dimensioning mechanism using the relaxed master program. The research develops decomposition algorithms, akin to the L-shaped or Bender's methods, which use parametric Gomory cuts to generate iteratively tighter approximations of the second-stage integer programs in a two-stage stochastic integer programming (TS-SIP) problem. Key details of the research. Problem class: the paper primarily focuses on TS-SIPs with binary variables in the first stage and general integer variables in the second stage. Methodology: it introduces an L-shaped decomposition algorithm driven by Gomory cuts that are parameterized by the first stage decisions, which ensures finite convergence. Contribution: the proposed methodology is noted for its flexibility and ability to scale better with an increased number of scenarios compared to solving a single large deterministic equivalent formulation using general-purpose solvers. The aim of the article is to illustrate the algorithm using a prototype and excluding any unnecessary features, first by implementing algorithm 1 in MATLAB, and later by implementing algorithm 2, which includes a complete dual simplex lexicographic method to solve the subproblems. Master problems are solved using Plex-Brocken bound. Second-stage cuts are Chittle-derived cuts, which are equivalent to fractional cuts and ensure integer cutoff coefficients. The example in Sen et al. Is a variation of an example by Schultz et al. The image shows the description of example 1. The variable R is a continuous artificial variable that ensures the relatively complete recourse property. The cut generation in Sen, S, and Hegel, J is used. This algorithm is called D2. The algorithm of the authors is called. The D2 algorithm involves the solution of larger dimensional linear CGLP programs and convex on the right side. On the other hand, the generation of cuts in algorithm 1 is relatively inexpensive. The algorithm can hot start the dual simplex method for the subproblems of the scenario, using the base generated in the previous iteration. In total, only 13 lexicographic dual simplex pivots are performed in the second stage during the execution of algorithm 1 in the MATLAB implementation. For brevity, only partial details of the first and second iterations are provided, which are used later to illustrate the partial implementation of branching and cutting. If a feasible solution is obtained, using the dual multipliers for the subproblems of the scenario, we construct an optimality cutoff and update the master problem. In this case, the upper limit UB2 is equal to -29, and the new master problem appears in the image. It illustrates how globally valid cuts can be generated when the branch and cut are incorporated into the second stage problems using example 1. Focus attention on iterations 2 and 1 and abandon dependence on y. We add the cut to SP1 to obtain a fractional solution equal to the vector minus 25.556, 1, 0.2222 and 0. We can add a cut at the root node of a partial branch tree and cut for the scenario subproblem. Then we create two new branches with y greater than 0, and y less than 1. Solving the linear relaxation of the first node, we obtain a fractional solution and equal to minus 24.75, 0, 1, 0.25, 0 and 0. The source row corresponding to y0 is in the image. The image shows the description of example 2. Tables 3 and 4 show the description of example 2. Table 3 shows that 9 cuts were generated for the single cut version. Table 4 shows that 13 cuts are generated in the iterations performed when a round of cuts is added in the second stage. However, the round of cuts approach requires only 4 iterations to end up with an optimal solution. To be able to compare the performance of the algorithm against the deterministic equivalent formulation, 4 larger instances from a variation of example 2 was generated. The goal of this test is not to compare the performance of the algorithm with commercial MIP solvers, but to check how the decomposition scales compared to solving the problem directly without additional features. Approximations constructed by algorithm 1 for example 2. The 4 black circles represent the points evaluated at the extreme. In 1a we plot the objective value of the initial linear relaxation of the second stage problems, which provides the best approximation available at the beginning of the algorithm. In 1b, 1c, and 1d, in addition to linear relaxation and the 4 feasible points for the SIP, we represent the functions z3, z5, and z7, respectively. The figure highlights how Gomory's segment survey allows us to avoid representing subadditive functions in the master problem and instead construct affine approximations of the second stage value functions. Table 5 shows the results of the comparison of our algorithm against 2 diarent settings of Plex 12.3 on the deterministic equivalent formulations. In this table, the meaning of the columns is Sin shows the number of scenarios in the instance. Obj indicates the optimal objective function value. Columns, vars and cons indicate the number of variables and constraints in the deterministic equivalent formulation. GDDS, single cut, and GDDR, round-off cuts, report the number of iterations of the decomposition algorithm with Gomory cuts, followed by 2 numbers within parentheses. The first number denotes the total number of non-root nodes overall iterations explored by the Plex's branch and bound tree for the master program, stage 1, with cuts, presolve and heuristics turned off. The second number denotes the total number of Gomory cuts added in the second stage overall iterations. BANB indicates the number of pure branch and bounds nodes explored by Plex, and BAND plus GOM shows the number of nodes explored by Plex along with the number of cuts added in when we use pure branch and bound with Gomory cuts. Since our algorithmic design includes only pure branch and bound, first stage, and pure cutting planes in the second stage, our comparisons with Plex in this section is also done with comparable settings to exclude any extraneous features. The implementation on instances of the stochastic server location problem, SSLP with at least 50 scenarios. These instances are available online as a part of the Stochastic Integer Programming Test Problem Library, SIPLib. Table 6 shows the size of the deterministic equivalent formulation, DEF, and the sizes of the subproblems, sub, of the test instances. In the table, cons, bin and int denote the number of constraints, binary variables and integer variables, respectively. Table 7 report the performance of Plex 12.4 with default settings on the deterministic equivalent problems. The time limit was 1 hour. The table reports the total number of cuts generated by Plex, the number of branch and cut nodes explored by Plex and the end gap at termination. We note that out of the 11 instances tested, Plex solves 6 instances of the defs. Since the default optimality tolerance for Plex is 0.01%, instances with end gap of 0.01% are considered optimal. In the largest case, the runtime ratio is 1 to 3.529 in favor of Gomory cuts. Table 8 reports the results using the decomposition algorithm with the single cut implementation. The columns iter, m cuts, M nodes, S cuts, time, E gap indicate the number of iterations, the total number of cuts generated by Plex over all iterations for solving the master problem, the total number of branch and cut nodes over all iterations used by Plex for solving the master problem, the total number of Gomory cuts generated in the second stage, the solution time and the end gap at termination. If no significant improvement is made in the lower bound or percentage gap in 50 iterations, we perform one upper bounding step by solving the scenario subproblems as integer programs and terminate the algorithm. The tolerance to check integrality for cut generation is 0.000. The experiments find that a smaller integrality tolerance gives rise to invalid cuts. The algorithm performs better than solving the def directly on all instances tested. For largest instances, the deterministic equivalent is very large, and Plex does not perform branch and cut and only uses cutting planes. The image shows the decomposition algorithm with parametric Gomory cuts for two-stage SIP. The algorithm is applicable when there are continuous variables and general integers present in the first stage, but their coefficients in the technological matrix are zero. Albert Einstein thought that imagination is the highest form of research. Thank you for your attention.